No, I will introduce you first, but okay. All right. Welcome, everyone. Thank you for joining today. This is our first seminar for Spring 2025 in our seminar series, Viceroy Sizer. I hope your semester has been good start and you are staying warm in this cold temperatures these few days. It will soon be spring, trust me. And we have today the first session in the seminar series, and our speaker, it's a great pleasure to introduce, is Dr. Bo Liu, who is relatively new assistant professor in the School of Engineering and Applied Sciences at Washington State University Tri-Cities campus, where he joined in 2024 in August. He received his PhD and from the Mike Weiger's Department of Electrical and Computer Engineering at Kansas State University, where he also worked as a postdoc and research assistant professor. He holds a master's and bachelor's degree from Harbin Institute of Technology in China. And in the summer of 2018, he spent as a graduate research intern at the National Renewable Energy Laboratory. His research spanned a number of areas, including cyber-physical security power systems, which is the subject for today's seminar, machine learning applications, and state estimation in smart grids. So what Dr. Liu will do today will be explore cyber attacks and defense strategies in smart grids. And he has been told that we have an audience that comes from different backgrounds, most of them being in computer science and cybersecurity and management and information systems. So he will begin by introductory material, and then the focus will be on machine learning detections that are used but are not sufficient and how to overcome that limitations. So our seminar, like we always do, will last for 50 minutes. The last 10 minutes will be left for Q&A. And so while the presentation goes in the first 40 minutes, if you have questions, you can put them in the chat and we will entertain them towards the end. And those of you who are familiar with this seminar, you also know you have to wait until the very end so that you get a chance to give feedback with the survey link. And James will put that when the time comes. Welcome again, and thank you very much, Wupu, for joining us this afternoon. I will let you get started.
Thank you for the introduction. In today's seminar, we will explore different cyber attacks in the power system and the defense strategy in the smart grid. Yeah, and also we will discuss whether machine learning detectors they are sufficient to detect attacks. Okay, so here is the outline of today's presentation. We will introduce 4 cyber attacks in the smart grid, and also introduce 3 defense strategy in the smart grid. And the last, I will present my work on modeling highly stealthy FDI attacks. So in the modern power system, renewable energy, they are widely used. According to the Department of Energy, by the 2030, there will be 20% total energy generated from the wind and 14% energy come from the solar. So this number definitely will keep increasing in the future. However, we know that renewable energy, they bring the vulnerabilities and uncertainties to the power system operation. So with high penetration of renewable energy, the modern power system is become much more dynamic than the traditional grid. It requires much more data communications and also more controls. So smart grid is a cyber-physical system which composed of physical system, communication system, and the applications in the control center. Let me use my pointer here. Okay. So in the physical system, it is composed of generation, transmission system, distribution system, and consumption system. In the traditional power plant and the renewable power plant, such as a wind farm and solar farm, they generate power and transmit through the long transmission line in the transmission system, and the voltage is stepped down in the distribution system, and provide power to the commercial customer, residential customer, and the industry. Okay, this is a physical layer of the power system. In the physical layer, we place a lot of sensors to monitor the status of field device, and the measurements of these sensors will send to the control room through the communication. In the control center, it will receive measurements, and the measurements will be used to calculate the voltage of the power system. And based on the voltage, multiple different functions, such as economic dispatch, demand response, energy trading, they will use this voltage information to generate control signal. And this control signal will send back through the communication to the generators and switches in the system. So you can say that the whole smart grid is a cyber physical system. To realize this system, Internet of Things and information communication technique, they are widely used. So these devices, they bring convenience, but also provide a huge attack surface for the cyber physical attacks. So according to the Department of Energy, between 2011 and 2014, United States Energy Department received 362 power interruptions reports related to the cyber attacks. Even though in the power system, the DNSP3 and IEC 61850, these protocols are used in the communication layer, but not all the packets are encrypted during the communication. So lack of encryption highlights the cyber vulnerability of a power system, and it provides the attack surface for the cyber attacks. So here I will briefly introduce a SCADA system. SCADA system, we call it a supervisory control and data acquisition system, SCADA system. They collect, analysis, and visualize the power system data. So one key function of SCADA system is supervise the whole system in real time, including the meter readings and the status of sensors. So here is the structure of the SCADA network. It is composed of host server, human machine interface, communication devices, outstation hardwares, and a local substation processor. For the local substation processor, we have the RTUs, remote terminal units, in the substation, and this substation is equipped with this device to collect various types of measurements from the field. And also this RTU device is responsible for transmit these measurements to the control center. So more recently, the intelligent electronic devices, they are replacing the RTU device, but they are also do the sending the measurements to the SCADA system. Okay, based on the system status, various application in the energy management will generate a control signal, and the control signal is sent back through the communication system, through the SCADA network to the programmable logic controller to control different devices. Okay, so here is introduction for the SCADA system. And here I provide several figures. This is a substation of the power system. Inside of the substation, we have the RTU device to transfer the measurements to the SCADA master station. And this SCADA master station will present and visualize the measurements data in the control room. Control room have other functions to send the control back to the substation and the field devices. Okay, next I would like to introduce what is a power system's estimation. The estimation input is SCADA measurements, and his output is voltage of each bus. So in the right figure, it is a HV 14 bus system. You can consider this is a small power system, and this line represent a bus, or you can represent a substation. So we have 14 bus, 14 substation in the grid, and in this grid, in this system, we have multiple. This circle means the power flow measurements on the transmission line, and also for the buses, we have triangle represent the power injection to these buses, to different buses. Okay. So SCADA system collect all these measurements and formulate as a vector, which is input for the estimation. So for most common stats method is a weighted least square method. It uses the SCADA measurements to calculate the optimal voltage estimate of each bus. Right? It means the estimation will calculate the voltage of each substations. So why do we need a estimation? Because we receive a lot of measurements, and also in the measurements we have measurements noise, and it could be large measurements errors. So we use the estimation to reduce the impact of noise and errors and provide the best estimate results. Another thing to mention is in the estimation, here is a estimation structure. We also have the bad data detection. It is used to detect the large measurements errors, and also it can be used to detect attacks. Okay. So here is a multiple blackout due to the cyber incident. We can see that the timeline is from 2003 and 2015. This first file blackout, I want to highlight first file blackout there happened due to the cyber incident, like the alert system failure, communication disabled, function disabled. But in 2015, Ukraine blackout, it happens due to the cyber attacks. Attacker switch off the breaker remotely in Ukraine electrical power system with help of malware black engine Trojan. So more than 30 substations, they were disconnected, and more than 200,000 customers, they lost the power for more than 6 hours. Since the 2015 Ukraine blackout, the power system have become a prime target for attacker. There are major cyber attacks against the power system between 2010 to 2022. We can see that cyber attacks happens more frequently. And the recent cyber attack like Raven and Enercon, this indicates that renewable energy resources are frequently targeted. So we can see that cyber attacks can cause damage to the physical system and also trigger a widespread blackout in the entire system. So it's necessary to analyze cybersecurity and develop defense algorithm in the power system. Okay. Here in this section, I will present 4 cyber attacks in the smart grid. So cyber attacks can be categorized into 4 types. The first type is data availability attack. So this attack targets on the communication channel, and for example, like denial of service attack. This attack focuses on the communication layer, and they are pure cyber attacks. They don't involve any power system models. So you must be very familiar with denial of service attack. Here I just briefly go through this denial of service attack in the power system. So this denial of service attacks can aim to disrupt the communication between the control center and the sensors or actuators in the field. The denial of service attacker, they are not required to have the knowledge of the power system configuration, or they don't need to have the capability to manipulate the control or measurements data in the communication layer. So this attack consequence is that system operator can easily notice the attack due to lost the measurements, but the operator cannot mitigate the attack since they cannot send control signal to the actuator in the field. One example of the denial of service attack is incident of Ukraine power attack. Attacker opened the switches, and then the denial of service attack is launched such that the operator cannot send the control signal to reclose the switches. That is denial of service attack. The second attack type is it's a control signal attack. Here, this kind of attack compromise the control signal sent from the control center to the field devices. Okay. This attack is more like a direct attack. They use a Trojan to steal the credential. The attacker can send a compromised control signal to the field devices. This incorrect control will cause physical damage to the field devices and also cause the power system operation issues. And the third attack is a measurements attack. Here. This attack compromises the measurements sent from the field devices to the control centers. This kind of attack is more like an indirect attack. They change the measurements so that they will mislead the power system operator about the system voltage and make a mistake in their operation decision. And the mistake decision will lead to the system losses and actual economic issues. The last type is a control signal and measurements attack. In this attack, attacker compromise the control measurements, control signal and measurements at the same time. So this attack require more resources because they compromise both measurements and the control signal. The idea is they send the incorrect control to the field devices and cause some issues, but they will modify the measurements so that it covers what is going on in the physical system and make the system operator think everything is okay. So this is 4 type for cyber attacks types in the power system. And now let's look into the second type, the control signal attack. So first, control signal attack, we call it Aurora attack. It's introduced by Idaho National Lab, which is where attacker can maliciously open and reclose the circuit breaker of a generator by injecting a series of compromised control command. When the generator disconnected from the grid, the generator becomes desynchronized. And this attack is designed to reclose the breaker before the generator protection system responds to the attack. So every time the breaker was reclosed, the different frequency and the different phase angle between the generator and the grid, they will result in a high torque and a high current. This torque and current can damage the generators. And this attack will close and reopen this breaker multiple times and until the generator is damaged. So this is a Aurora attack. The second control attack is a pricing attack. So here I need to briefly introduce the concept of demand response in the power system. So demand response is a strategy of adjusting the electricity demand according to the supply condition. So in the price-based demand response, during the peak demand hour, the electricity price is high. In this case, the customer will reduce their consumption. And during the normal demand hour, the electricity price is low, so that the customer are more willing to consume power. In this case, you can see power system operation based on the demand response is a control algorithm, right? And the control signal is a price. So the pricing attack is attacker can send the scaled value of true price or use an old price on the price signal, so that the customer will use the incorrect price signal and mislead their energy consumption. So this attack will cause the mismatch between the generation and the power consumption. This power mismatch will cause the operation issues, for example, the frequency issues, and also cause the over generation economic losses. So this is the concept of pricing attack. Another famous attack, control signal attack, is a wind shark attack. This attack is against the wind farm. What?
We lost your slide.
Yeah. Me share the
You may share
slides again. Share the slides again.
Great.
Okay. Yeah, because wind energy is a predominant source of the renewable energy, and also it has SCADA system to control the wind turbine and the substation. This IEC 61400, they define the communication requirements for the wind plan, and use this standard system operator can remotely set the wind turbine on, off, or idle. And also can conduct an emergency shutdown. Here, I would like to highlight what is an emergency shutdown. This emergency shutdown is when system operator detect a condition that could damage a turbine if it continue to operate. For example, when the tornado happens or a high wind happens, the emergency shutdown can be used to make the turbine stop to rotation. It's a mechanical brake in here. There's a mechanical brake in the wind turbine. It's like in your highway. It's like a brake in your running car. If you met emergency in your highway, you can step the brake pad to the end. But we know that the gear and the gearbox in the turbine will be impacted by the emergency shutdown. So emergency shutdown is not graceful, and the engineer would not like to use the emergency shutdown. But attacker can utilize this emergency shutdown to cause damage to the wind turbine, right? They can utilize a Python-based tool to hijack the turbine and send the emergency shutdown command to the turbine, and to use this to reduce rotation. And after the wind turbine restore to rotate, attacker can launch the emergency shutdown again and again until the gearbox is damaged. Yeah, this is a concept of wind shark attack. Okay, next I would like to introduce the third attack. Is a measurements attack. false data injection attack is a very major measurements attack in the power system. It manipulates SCADA measurements received by system operator, and the attack target is cause a bias in the operator's estimations. For example, if attacker want to compromise the voltage of these 3 buses, she need to compromise all the measurements in this attack area. And also these measurements need to follow the physical law of power system. Otherwise, these measurements, this attack can be detected by the bad data detection being introduced previously. And so attacker need to compromise multiple measurements in a coordinated way. And how we can construct this attack? The slides stuck. Oh, here. So here is the FDI attack mathematical model. So if you want to, attacker want to inject a vector A to the original measurements, you need to follow the power flow equations. And here X is original states before the attack, and use X plus delta X represent the malicious system voltage. And the attacker's target is to mislead operation to X plus delta X. So you need to calculate the A vector using this equation. In this case, the attack is stealthy to this BDD, the bad data detection. And the knowledge requirement of this attack is that system attacker need to know the system topology, the line connections, the bus connections, and also she need to know the transmission lines impedance, which this topology and line impedance is represented by the H functions. And also attacker need to know the system buses to construct a stealthy false data injection attack. Okay, lastly, I would like to introduce a line outage masking attack. So in this attack is a control signal and measurements attack. In this attack, attacker can physically disconnect some lines in the operation power system, and this disconnected line will result in short-term damage like the voltage violations and the transmission line power overflow. And at the same time, attacker can launch the false data injection attack to change the measurements so that in the power system control room, they will receive the incorrect measurements, and the system operator will not find out the issues in the power system operation. So this is a concept of line outage masking attack. So here I would like to introduce 3 defense strategy. First, this 3 is measuring, securing the measurement sensors, moving target defense, and data-driven approach. So the first method is use the protected sensors to collect the measurements securely. Okay, because Cyberattacks require the right access to control or measurement signals. A very natural approach is to select and protect critical sensors. But there is a trade-off. If you protect all the sensors, it will be expensive. But if you protect only a few sensors, it may be leave the attack surface for the cyber attacks. So we need to optimally select and protect sensors through the graph analysis and optimization problems. So we need, so after using this proposed method in this paper, if we want to protect the given buses in the set D, we need to minimize the number of protected sensors in the objective function. And this constraint ensures that the given bus cannot be compromised by attack under the protected sensors. But we know that you can see that this optimization involves the rank, so that this optimization is NP hard, and we cannot solve it directly. In this case, a graph analysis is need to convert the problem to minimize the Steiner tree problem. Yeah, if you want to, for example, this is 14 bus, all the measurements in the 14 bus system. If you want to protect bus 12 and bus 8, we need to form a Steiner tree to cover these two bus and also the reference bus 1. So this is all the measurements need to be protected by the sensors. Okay. And next, I would like to introduce a defense strategy here. This is my work during my PhD. So in the moving target defense, it actually changed the system configuration to invalidate the attacker's knowledge about the true system configuration, because attackers need accurate system configuration to launch the stealthy FDR attack. If you use the defects devices to change the transmission line impedance, then the attacker will not have accurate line parameters, and then his attack is not stealthy anymore. But the concept is simple, but if we want to implement this moving target defense, we need to solve two problems. First one is MTD planning. It solves the placement of FAC devices. It means which line we need to change their impedance, because in power system there's thousands, hundreds of transmission line. We need to select the optimal line to install FAC devices. And the second issue is how to set the set points for FAC devices, because in the system we have multiple FAC devices based on the load condition, how we can optimal set the set points, consider the load condition. Okay, this is two issues. And we developed 4 metrics to evaluate MTD performance. First is a cost. This cost includes the capital cost, namely the number of FAC devices in the MTD planning, and also the operation cost, such as actual generation cost and the system losses due to the MTD. The second metric is detection effectiveness, which is a most important metric for the defense method. It is unknown in the literature. Detection effectiveness is related to operation or planning. So our work proves that MTD planning determines the detection effectiveness. And the third metric is stability. Since changing line impedance can be considered as a disturbance to the system operation, so MTD operation need to consider and ensure the voltage stability. And last metric is the stealthy of the MTD, because smart attacker can detect the existence of MTD. That's from the defense perspective, it's necessary to make the MTD hidden to alert attacker. So to achieve this hiddenness, the placement and the operation must be designed together to achieve a hidden MTD. So due to the time limits, I will briefly introduce how we can optimally place FAC devices considering the cost and the detection effectiveness. Okay. So in our MTD planning, we have 3 objectives. First is we want to maximize his detection effectiveness, and also we want to use a minimum number of defects devices. And at the same time, the defects devices is originally used to manage the power flow, reduce the system losses. So we also want to consider the economic benefits of FAC devices. So based on these 3 requirements, we use the graph theory-based proving and analysis. We convert this objective to 3 requirements. Okay, the requirements is black graph. It means the graph of all the black line. It means the black line means we don't install any effects on this transmission line. Okay, and the red graph means we install effects on the transmission line, and this transmission line can be considered as a red graph. Okay, and another thing is fax devices is installed on the lines with high loss sensitivities, because high sensitivities can contribute to reduce the power system losses. So we propose an algorithm to find out the solutions satisfy these three requirements. If you ignore the red lines in the system, all the black lines, they form a spanning tree. And also if you ignore the black line or the red line, their graph has no loop, right? So this is sufficient conditions to achieve this MTD planning objectives. In this case, it achieves the maximum detection and use the minimal number of fact devices. Okay. Yeah, last I would like to introduce a machine learning detector in the attack detections. So supervised machine learning detector use historical measurements collected from the SCADA system as a normal data and use the generated fact FDI attack as a compromised data in the training stage. So classic detector can detect attack based on the fact that normal data and the compromised data, they tend to be separated in the certain projected space. In this case, defender can conduct the PCA dimension reduction and project high dimension data to the 2D space. And it is seen that the normal data form a cluster while the attack located outside of cluster. In this case, the attack can be collected by the classic supervised classification method, such as supervised support vector machine, logistic regression, and the MLP. Okay, this is a classic machine learning detector, but this classic machine learning detector suffer from multiple issues. First is our SCADA measurements, they have very high dimension. Another issue is measurements, they have its own pattern. Second issue is because we in the training stage we have a lot of normal data, but the cyber attack didn't happen frequently. We don't have so much bad data, attack data. So we lack of attack data. It caused the imbalanced data in the training stage. And another issue is in the machine learning functions, they didn't consider the power system configurations. They don't consider line connections. They don't consider the line impedance. So how to deal with it is we can use deep learning detectors. They can learn the spatial and temporal correlations of historical data and detect the traditional FDI attacks that is different from historical measurements. For the high dimensional measurements, we can use the CNN to deal with it. And for the measurements pattern, we can use the RNN to learn the pattern and then detect the attacks. And for the imbalanced data, we can use the GAN network and autoencoder. They can be used to construct the semi-supervised or unsupervised detectors. The last challenge is how to use the power system configuration. We can consider power system configuration as a graph, and then the graph neural network, they can integrate this power system graph into the detection. So there's a lot of application of the deep learning in attack detection. So here I briefly introduce their challenge and present some directions. Next, I would like to introduce my work in attack modeling. So this attack is designed to remain stealthy to the classic machine learning detectors. We would like to explore what's the limitation of machine learning detectors and how, from attacker's perspective, how we can construct an attack that is stealthy to the machine learning detectors. And at the same time, it should be remain high impact on the power system operation. Yeah, we developed matrix completion FDI attacks. This is the first attack designed to remain stealthy to the machine learning detectors. And we apply this matrix completion to learn the temporal correlations of history measurements and also maximize the voltage bias to cause sufficient negative impact on the power system operation. First, I would like to briefly introduce matrix completion. It's a technique to estimate the unknown elements in incomplete matrix. We know that here is a image of our brain. We can consider as a matrix, right? If we randomly delete 50% of pixels, it becomes incomplete matrix. And the matrix completion technique can recover the incomplete matrix to the complete matrix, right? So this is the output of matrix completion. We can find out that it is very likely to, it's very similar to the original matrix. Right? Here's the formulation for the matrix completion problem. We minimize the rank of incomplete matrix X and also let the elements in X equal to the known elements in M. Incomplete matrix. Okay, so this is a formulation. So how we can use this to construct an attack is we need to formulate a matrix, historical matrix. So we formulate a historical matrix zero, and here is a timeline for the estimation. SCADA system collect measurements every 10 minutes, and from attacker's perspective, we'll collect these measurements each time step until we want to launch attack at time step T. Okay, and here different color represent different measurements type. And we want to, for example, we want to compromise these three buses in the system, and all the related measurements, we set them unknown in the matrix and let the matrix completion to fill these elements. In this case, the compromised measurements will follow the temporal correlation of historical measurements. And also, these first two constraints and the objective function, they come from the matrix completion. And also, we want to maximize the voltage bias. Okay. Here is a third constraint is the linearized attack equation. And also we set constraints about the voltage duration. So after we solve it, here's our experiment results. On the left figure, it is traditional FDI attacks. We can see that normal measurements formulate a cluster, but the traditional attack, most of them located outside of the cluster, and so that they can be detected by the SVM detectors, like 47% attack can be detected. Some attack cannot be detected because this attack magnitude is very small. It's very close to the original measurements. But for our proposed matrix completion attack, we can see that they are located inside the cluster, such that the detector can only detect 7% of the proposed attack. That's because some attack is on the boundary, so that it could be detected by the detector. So here is the impact of the lambda weight in the on the attacks. We can see that even though we increase the lambda value, we will have a larger voltage bias, but still their nuclear norm is low, and accordingly projected in the 2D space still inside the cluster. So that also shows stealthiness of proposed attack. And last, I want to talk about the detection of this attack. Yeah, we introduced 3 detection methods. First is we use protected sensors. Yeah, in this matrix completion attack, we designed this attack for remain stealthy to machine learning detectors, but we need to compromise the multiple sensors. If you use protected sensors, then we cannot launch such an attack, right? And another thing is we can use moving target defense to detect this attack, because in our attack construction, in this mathematical model, this H matrix contains the accurate line impedance information system configurations. If you MTD change the line impedance, then we will use the wrong H matrix, and accordingly, the residue in the bad data detector will increase and detected by BDD, bad data detector. So that is how we can detect such attacks. So in general, we need to develop some multiple layer for the defense. We can protect our sensors and introduce a proactive defense, moving target defense, and also in the application layer, we can use a machine learning detector to detect attack. So core system needs multiple layers to detect attack. Yeah, that's my presentation. Any question?
Yeah, thank you very much for that nice overview, Bo. You've covered a lot of ground. We've got some time for questions. So anybody who has got a question, you could unmute and ask, or put your question in the chat, and Dr. Liu will answer your questions. Anybody who's got questions? And in the meantime, James will probably put the link for the survey so you get to complete it right after the session is finished. Anybody who's got questions? So there are some nice connections to those of you who are in computer science. Spanning trees and Steiner trees showed up in a graph where you would want to know the edges that would cover everybody. That's what a spanning tree would do. And then there was a nice connection to matrix completion, which is a technique very useful in machine learning and data science. You might have seen them in recommender systems or in image completion and things like that. And so that's another technique that has showed up. So you don't have to know a whole lot of power systems to be able to contribute something significant as a computer scientist, is one of the messages I would take away from this. And a lot of new things to learn about how attacks would come and the different types and how to design strategies against them, defense against them. Any quick questions from anyone? That was very clear. I appreciate the time you took to.
Yeah, I found out that I prepared too many slides.
Yeah, you're fine.
I don't have enough time to provide more deeper information.
I know. I can see that. That was rich material. We will make the slides available to students. So, Bo, you will send us this, and we will also make the recording available to students. Does anybody have any questions? Let me see if there is anything in the chat. There is one question already. I'll start with the second. When you provided the example of a formula for the graph, what is the code in? Is it mainly C or another language? I think this is referring to your moving target detection planning. That's a quick question on what language you use to, I guess. Not sure if I understand the question, but.
Yeah, first question is a CNN. Yeah, there is a here. There's a transaction papers. First one use a one-dimension CNN to detect the FDR attack. Yeah, if you're interested, I can provide the link for the paper. I can provide the paper. They just use the one-dimension CNN. They can achieve very high efficient accuracy. And also, this is the first work in the literature, but in the later work, they apply all kinds of to detect attack. Yeah, there's a lot of work in the they try to combine and use CNN in different way. But for example, they can use a autoencoder to reduce the dimension and then use CNN. There's a lot of research there. And
can you comment quickly on the second question? Yeah.
Oh, an example from them. Oh, is this? Yeah, in this MTD planning, I use Java to implement this algorithm because in Java they provide multiple package to deal with a graph, so that you can just use the graph to find the minimum spanning tree to utilize their library.
Okay.
And yeah, it saves a lot of time.
Yeah, but the pseudocode here is not language sensitive. I guess the question was more like if it was written. This was more of a pseudocode, but in your implementation, boy, it sounds like you use Java. I'm sure you are not very sensitive to performance and things like that. You don't do this in real time for online kind of decision making, so you probably can afford to run things in Java, I'm sure. So. Any other quick questions in the last 1 minute? All right, I think we are over time. So thank you very much for attending. Make sure to fill out the survey. Thank you very much again, Boo, for taking the time to have a nice introduction and also some of your recent work. We'll be in touch and we will see you next time when we have in 2 weeks time from now for another seminar. All right.
Yeah,
thanks, everyone.
Thank you so much. And if you are interested, you can send me email. Yeah, I would reply in time.
All right. Thank you very much.